Then we'll see how much I will also provide you this lecture. So we have been coding in Python, and Python is one of those languages that you can actually run on large supercomputers, because Python is platform independent and you can run them on different platforms, which is what supercomputer is one actually large application of Python, especially with machine learning today. Much of the machine learning tools is actually Python based. It uses C++ and a lot of the advanced GPUs, but you actually write your machine learning code often in Python. That will give you there's an introduction here to what supercomputing is, give you some background on HPC history, how you build supercomputers, Linux and HPC. We'll probably skip the statistics here, how you use clusters, and some background on what Lunar, where I come from, what we have done, built in clusters. So supercomputing is a broad term for one of the fastest computers currently available. So some computer usually done to scientific simulations, graphics, analysis of geological data, and in many areas where you have simulations that are really heavy computational loads in. But I have a short explanation. So it's time dependent. A supercomputer a couple of years ago is what you have in your laptop today. But I would say my quote is a computer that offers much greater capacity than a desktop computer offers at present, or have properties that a normal computer architecture can't offer. So it could be that you have many more cores than you have in your laptop. It can be that you have terabytes of internal memory, or you have large storage system that you can store large data that you want to analyze. Usually combine that becomes a supercomputer. So why do we need those? Yeah, we often have problems that require large resources today. So if you find out this simulation will take 1 month and I need a result in 1 week, that you can't solve that on your own computer. You need to do something about that. And if you use a supercomputer, you can scale that up and use multiple CPUs at the same time and reduce the simulation time. It's also possible to do more simulations. For example, if you do work with car and airplanes and you want to test them, it's very expensive to do real prototypes. So by using supercomputers, you can do more simulations in the computer before you do actual crash tests. And another one is, for example, if you want to foresee weather, you can't wait for the simulation to finish. You need to be finished before, so you can predict the weather. Otherwise, it's kind of useless. So many of the largest computers in Sweden is actually running weather simulations for forecasting. And that's why they're big, because they want to make a precise forecasts, and you need a lot of compute power to actually make the resolution very low. So just some areas for supercomputing: meteorology, crash simulations, very popular at Volvo, Saab, and other industries. Usually they require really large computers to do, because they have millions of degrees of freedom, and millions of it is equivalent to the equation system you have to solve. And then you have to do a time-dependent solution as well. So it requires a lot of computer power to do that. Fluid simulations, also very computational demanding, especially if you want to kind of resolve the finer turbulence in a good way. You need more higher resolution mesh, which is in larger equation systems. There's a lot of medicine simulated, drug discovery, data analysis, structural mechanics, very popular also, supercomputing, especially if you want to do time-dependent simulation with advanced material models. All that builds takes time in your simulation code, which requires you to have larger computers to do that. Also, lot of memory, because many of the mechanics applications require a really large amount of memory to solve. Chemistry, molecular simulations, very popular. They can scale basically to the largest computer system in the world, no problem. So the more complex the moleculars are, the more complex the simulation has to be. So some history. So I'm going from 64, I didn't go more than that. So many of the supercomputers, the scale you measure is usually how many floating point operations per second you can do. So if you see here, this is a CDC 6600. All these things are, I think this middle part is a computer, a printer, and terminal. If you compare, I think this is old. 3 gigahertz PC is 6 gigaflops. I think we are 1224 gigaflops per second on a normal computer today. You can see that 9 megaflops, 64. In 69, we had 40 megaflops and a computer that took up a complete room. 1976, we got a Cray, 160 megaflops. We're still only 10% of PC today. And this is actually a fluid cooled thingy. So it has a fluoride thing to cool the circuits in. But they put a nice couch here, you can see that. Cray XMP, I think this is one of the first computers we got in Sweden. And it was heavily protected by the military because the US government didn't trust us. So it was locked, I think it was in Linköping they had one. So we have 235 megaflops. A lot of the simulations for the JAS Gripen plane was done on the Cray. 1986, the reason I bring up this computer, this was the first computer we had at Lund University, supercomputer. So this was IBM 3090, we had 110 megaflops. And this VPS stands for Vector Processing Facility. So this was actually just a single processor, but the thing what is really good is it could process large vectors of data at the same time. So you could give it an array and it could give the same operation on the entire array. So it was a single processor, but it could handle multiple data. 1989, we got the Cray Y and E, and now we are getting into the gigaflop range. Also, I think we had it in Linköping. 93, now we are exceeding the normal PC again, Cray T3D, 13.7 gigaflops. 97 was an interesting year. This is actually a PC-based cluster, one of the first commodity clusters built. So this was built on normal PC hardware. Also servers that were Intel-based, put in racks, and it had 2.38 teraflops. This was one of the largest facilities overall, the Earth simulator in Japan. So it was meant to simulate hurricanes and storms and weather. I'm not sure what it's sent for. I think the numbers have come okay. Then we have a 2004 Red Storm. It had 41 teraflops. And this is an interesting thing. It has red and black and white. This is a military system, so you can actually physically divide it up into different partitions depending on if you're running military applications or civilian. Blue Gene, IBM's specialized cluster with smaller processors, but more of them. 596 teraflops. And then we go back to Lund again. So this is our Malaric system. 40 teraflops. We have the Jaguar with 1.64 petaflop. So now we are getting into really small computer. You can see also all the difficult to see here. Very all this stuff here is cooling. So many of these computers, they are in the megawatt range. So they require a lot of power. Lunark, we have 250 kilowatts in our computers. But these US labs, they are, I think the large one are 10 megawatts. So it's the cooling of these machines are really, really important. Roadrunner, 1.7 petaflops, IBM machine. Aurora in 2016, 240 teraflops. Stampede here is 19 petaflops in Texas. And then actually we are building, what is this animation? In 2023, so actually this month we are releasing the system called Cosmos, which is will be actually 1 petaflop in Lund. So that machine will. So we have built approximately the same size of systems all the time, but we have got more and more performance of machines for the same amount of power. So I will just quickly go through the architectures here. So there are different architectures of supercomputers. Single instruction, single data, that is something called a von Neumann machine, classical computer. Then you have single instruction, multiple data. That was the vector processor facility I showed you before. So that has a special processor for handling vectors and arrays. We don't have a multiple instruction, single data type of computer. But we have multiple instruction, multiple data, so those are multiprocessors, and those are actually what we have today in our cluster. So every server in our cluster has 2 processors with a total of 48 cores. Those are connected together with multiple servers in a network. So you have a hybrid of shared memory machines where you have processors that are shared memory combined with multi-computers where you have sending messages between the computers. So this is the main difference. If you have a shared memory machine, this is what you have in your laptop. You have one memory in your laptop and you have multiple processors working that memory. In this architecture, we build our clusters. You have multiple servers here with a processor and memory, and they communicate with each other using message passing into the Connect network. But usually today we have a hybrid. So on each of these here, we have multiple cores. So, and then they communicate with another server with multiple cores. So this is a modern supercomputer is a hybrid. Then we can have different networks here, connecting these computers together. Can have multiple. This is a very common one. We have master switches here, and you have the servers on the top here, and you have multiple level of switches. Some connections are point to point. Others are this kind of hypercubes. One thing with supercomputers, what you usually want to look for when you want to scale up on a supercomputer. Sometimes it's easy to believe when the problem goes faster and faster, the more number of CPUs you throw at the problem. And that's the ideal situation. This is this line here. You have the linear speed up. So if you have 40, it goes 40 times as fast. The normal, really good parallel application is this line here. So at 50, you don't get up to 40 times speed up. And then you have another application here. Speed up is less and less when the more processors you add to it. Then there are some problems that end up here. It doesn't matter how many processors you throw at the problem. You don't get more speed out than a certain number. So ideally you want to be here, but usually you're somewhere here. Yeah. There are some important stuff with internet as well, the networking between the nodes. You have something called bandwidth, that is how much data you can communicate with. So gigabit Ethernet is common in your house. In our computers, we have 25 gigabit Ethernet between the nodes, but we also have something called InfiniBand that is up to 100 to 200 gigabit per second network connections. But the important thing in our application is something called latency. And that is how long it takes for the computer to initiate communication between another computer. And in normal networking, that is really slow. But in supercomputers, this is really, really fast. So InfiniBand, which we use in our network here, we have really low latency. It's very quick to initiate communications between servers. And also, one thing that happened in the 90s was that Linux came to the HPC. So this guy here built the first supercomputing using normal PC boxes, connect them together using a network. By having an open source operating system, you could build a supercomputer and use the normal way of programming parallel applications and run them on a really cheap computer. Let's skip that here. So this is actually his first supercomputer built in a cupboard. And I will just skip through this here, and I will show you some of the. So when you use clusters, you log in either using a terminal or a desktop. You have software and compilers available. You have a shared file system to access the files. And what is special is to have something called a queuing system or job schedule. And you submit, this is a script. Basically what you do here is you call your program here, what you do on your command line in the terminal to run your job. And you specify here, I expect my job to take 10 minutes. And then you submit this file to the queuing system. It ends up in a queue. The scheduler looks at the servers available on the cluster. So here you have all the servers, 1 to 252. And here you can see I have a job that is wider, and it tries to place them in the queue as optimal as possible so that it will execute as quickly as possible. And I just want to show you some of the clusters that we have built. So this is the latest one. So we have 182 servers with 8,736 cores. Every server has 256 gigabytes memory. We have 8 nodes with A100 NVIDIA GPUs, 12 nodes with A40 GPUs, and those can do graphics as well. But we started like this. So this is a 64-node cluster using complex computers, connected using very standard network connections. The next cluster was total 7 was 128 Dell small form factor desktop that we connected together to a big cluster like this. And this looked better at the first iteration, but we had to move the cluster from one place to another place, and the networking was really not perfect when we put it together again. This is the first CERN cluster we built. So this first rack mount cluster looked like this in behind. So there's a lot of cabling going on when you do compute clusters. The CENTEN 210 nodes, the first 64-bit cluster, single core. So every rack server here was one core. A lot of cables. Miliotto was an IBM system with 1,000 cores. There was a lot of cables. We had to cool it with special rack mount coolers. This is Siri, which is a second generation grid cluster. This was blade chassis like this. And then we have Platon with cooling racks. And now we have Cosmos, the latest system today. So conclusion, HPC is important for science today. It enables you to do research to do large simulation. That can't be done on a standard computer, memory, network, storage. Enable much more simulation in a short amount of time, and reduce expensive real-world testing, enable AI and ML. So AI and ML today, machine learning, is something that supercomputers has enabled. You couldn't have done machine learning, all the ChatGPT stuff without supercomputers. So training the networks is actually the hard part.